Hello. In this video we will see Lab 11 Optics 1 Activity 2. So in the previous videos we were playing with Snell's law and we verified the refractive index using this law on different materials. Now we will use the focal length of converging and diverging lenses in this Activity 2. So how a thin lens works? Well, if we have a converging lens like this, light beams coming from the infinite as parallel beams to a place named focal plane. This is the focal plane, which is characterized by this lens. Okay? And we can build different lenses having different focal planes. If we have a diverging lens like this, what happens is that rays coming from infinite as parallel beams, they will refract, not converging by diverging, meaning that the focal plane in this case is on the same side than the object plane. And that's why we have the so-called a virtual image, as we will see. So how do we calculate the position and size of an object which is imaged by a lens? Well, we basically have to use three rays. One first ray, number one, will come from infinite as a parallel beam, and every light coming from infinite when passing through the lens will go like this, passing through the focal plane. So that's the first law of a thin lens. Okay, every ray coming parallel will pass through the focal plane when refracted from the lens. Second law is that the rays that go straight to the middle of the lens pass through without any deviation. This is similar to the example we saw in Snell's law. Beams which are perpendicular do not deviate, they go straight, perpendicular. This is the same case here for ray number 2. Ray number 3 is a ray that is passing through the object focal plane. As we can see, focal plane we have on both sides, on the image side and on the object side. So on the object side, if we trace a ray like this passing through the focal plane, it will go parallel on the image plane. It's the opposite as number 1, as you can see. Number 1 comes from infinite as parallel and will go through the focal plane. In number 3, we have the opposite. We have a ray going through focal plane and it will go parallel afterwards. At the position where these three rays coincide, that's what we have the image. And as we can see, for a converging lens like this, the image is inverted. If we place our eyes here, we will see an inverging lens, an inverging image. The law that governs this behavior is the so-called thin lens equation. The thin lens equation is something like this. S is the distance from the lens to the object. S prime is the distance from the lens to the image. And F is the focal length from the center to the focal plane. This is the law that governs this image creation. If we have a diverging lens, we apply exactly the same rules, but now since the diverging lens will create rays going away, the image, as we can see, is on the same plane as the object. That's why we call a virtual image. A virtual image is something we cannot get on a screen. It's something we can see if we look through the lens, but we cannot hear get this image on a image plane. If we place a screen here, the screen will block the light going through. So that's why we cannot retrieve, we cannot get this image. We can just see it. We just see it through the glass like this, okay? And exactly the same law governs the creation of this image. In this case, the image is smaller, as we can see, but the important thing is that it's not inverted. It's a direct image, okay? Same direction as the object, okay? But we cannot get it on a screen. We just can see it through the lens, okay? The only precaution you have to take when using this formula is the signs. What is the sign convention? Well, sign convention is S, which is the distance from the object to the lens, is positive when the object is to the left of the lens. That's a positive distance, S. S prime, which is the distance from the lens to the object, is positive when we are to the right. So if the image is to the right, it's positive, okay? If we follow this convention, then you can basically calculate the sign, positive or negative, depending on the radius, concave or convex, meaning that if we have a converging or diverging lens, and the type of image at the end, if it's a real image or a virtual image, okay? We can even calculate this using this formula. Y prime is the size on the vertical axis of the image. Y is the size on the vertical axis of the object, right? So this magnification, which is the ratio between the size of the image compared to the size of the object, follows also this rule. This minus takes into account the sign. Count it here. That's why for a real image created by a converging lens, M is negative, meaning that we have an opposite inverted image compared to the direct object, okay? While in a virtual image produced by a diverging lens, this minus will create, having a minus here as well for S prime, will create a positive image, a positive direction for Y prime. So let's do this in practice, okay? How can we do this in practice? Well, we will need some materials on our physical labs, like the optics track to place the objects, lenses, and light sources, some adjustable lens holder to place carefully the lens, some beam, as we did in the previous lab, some light source to get some beam of light, some mechanics adjustments to place the different objects, and a screen, basically, okay? Screen to get the image for converging lenses, okay? This is a setup. Like I said, we have here the lamp, the light source, the object just next to the lamp, the lens. With the mounting, we can move back and forth to get S and S prime at the position we want, and here finally we'll have the screen, okay? So we can even see a real experiment in this nice video.
What's this object here on the optics track here, JJ?
Well, Dan, it is a light source. There's a lamp inside here, and there is a translucent screen here that's illuminated by the light source that's inside. And what we're going to do is we're going to use this in our experiment as our object.
Looks like something you might see at your optometrist.
Yeah, that's right. There are lines on here to make measurements both left and right and up and down for additional experiments if we wanted.
And here in the middle, that looks like a convex lens, and that's something else that is at the optometrist. It's what he's studying in your eye, right?
Yeah, that's exactly right. This is a double convex lens or a converging lens that we're going to use in our experiment. We actually don't know what the focal length is. That's what this experiment is based on. We're going to collect some data and try to experimentally determine what the focal length of that lens is.
Okay, I think we need to measure the object distance and then the image distance to do that.
Right. Okay. So let's start with an object distance of 24 centimeters.
Okay.
And so that's the distance between the screen here and the lens. So this is our object distance. And I'm going to use the scale here on this track as my guide. 10, 20, 1, 2, 3, 4 centimeters. And now this lens should produce a real image.
But I don't see anything there.
Okay, so let's adjust this. So we're going to adjust this viewing screen until we see the image in focus. I'm going to kind of go back and forth until I find it. And that looks good right about there.
And so the image distance would be from the lens to the screen then.
Right. So once it's in focus, this distance is the image distance. And so this looks like 10, 11, 12, 13, 14, 15, 16, 17, 18.4.
Okay. Got that. So we should maybe move it apart another 10 centimeters or so.
Yeah, so we're going to collect some more data to help us determine this relationship graphically, right? So let's move this. Let's make this now, instead of 24, we'll do 34. So we'll add 10 centimeters. I'll just move that 10 centimeters. And then moving it made the image go out of focus. So we got to figure out what the new image distance is. So I'll just move that. And that looks about the most focus. And that is 10, 11, 12, 13, 14, 15 centimeters.
So it went down as that went up.
Right. That's right. Okay. Let's keep going. 10 more centimeters. So now, so we've got 10, 20, 30, 44 centimeters, right?
Right.
Okay. And then I'll adjust this. Right about there is the most focus. Let me just double check. Yeah. And this is 10, 11, 12, 13.6.
Okay. Should do a couple more here.
All right. We'll do 10 more. And then we'll move that. That looks like it's hard to tell sometimes when the image gets really small, but that looks like it's pretty much in focus. What do you think? You want to take a look?
That looks good.
Okay, so this is 10, 11, 12, 13.
Still going down.
10, 11, 12, 13. All right, one more.
One more should be good.
So we'll move that 10 more centimeters. And then we'll adjust this. That looks good right there. 10, 11, 12.4. 10, 11, 12.4, yeah.
Okay, that's 5 data points, and I've entered them into this capstone file, which you have access to. And so your job is to do the analysis, to look at the relationships between this data, make a graph, and come up with the thin lens formula and apply that to some questions.
So once we have seen the video with a real experiment, let's simulate this experiment. To do this simulation, we'll access to this nice simulator made by Physics Classroom. So when you click to this website, you will get to the simulator. You can enlarge the simulator if you wish. And you want to play with different objects. I like this object, the black arrow. Okay. You can change the size of the object. You can change the position of the object, just clicking on it and moving back and forth. That will change S. And you can change f, which is the focal distance. Okay? So your goal will be, as explained in the slides, to play with this parameter with certain input values for the object's position, object size, and focal plane. And using Excel or any other tool, you want to really check that these values are true. And also, you want to do a second thing. You want to try to understand why, when we get closer to the focal plane, you get this nice effect. The image is out of scope. Okay? You want to really see what happens when you get closer and closer and closer to the focal plane. Okay? So here are the things you must do again. You want to run the physics classroom simulator. As object, I want you to choose the black arrow. The focus initially would be something around 26.3 centimeters, depending on the resolution of your browser. Object distance, something around 40 centimeters. And object height, which is called h in this simulator, but we call it y in our formulas, around 10 centimeters. With these input values, you want to verify using the physics behind thin lens equations. You want to verify that the values for the image distance and the image height, which are s prime and y prime in our formulas, correspond to the ones calculated by the simulator. Okay? If there is any difference, of course, you want to provide this difference as percentage difference, as usual, right? Theoretical will be the ones you calculate, experimental would be the simulated ones, as usual, okay? And you want to also observe what happens when you move the object close to the focal plane, as we saw in the simulator, okay? And you want to try to explain why you get this behavior on the image, okay? As usual, do not forget to take screenshots for your lab reports. That's all you have to do to complete this activity 2. Good luck.